This is anaerobic. It does not require oxygen. But the downfall, without oxygen, pyruvic acid will degrade into lactic acid. So we run the risk of building oxygen debt. We run the risk of getting fatigued. We run the risk of getting tired. So examples, tennis, right? You hit the ball and you bounce around waiting for it to come back. The soccer, the short swims, those little guys. Then we've got aerobic respiration. So after about 45 seconds, 50 seconds, we've gone through and we've built up a lot of pyruvic acid from glycolysis. Now we need to disperse it, because if we don't get rid of the pyruvic acid, it's going to build into lactic acid, causing fatigue and problems with muscle activity. So we need to bring in that oxygen, throw it into the mitochondria with the pyruvic acid, getting a ton of energy for us. So we're looking at about somewhere between a minute 15, some as early as 50 minutes, depending on you and your body. We need to start breathing. We need to start bringing in oxygen so we can utilize pyruvic acid in the mitochondria so we can get a lot more ATP. So we switched over into aerobic respiration. And our example, like we talked about last week, by the time we get to the second floor of the building, we're breathing heavier because we've been walking for about a minute, and that's put so much work on us that we need to get more oxygen in so we can generate more ATP. So anything that is prolonged activity. So things like jogging, marathon running, stuff like that. They're going to rely on this. That's why they don't go very fast. Okay? You can probably outrun a marathon runner doing his race because he's in it for the long haul. He's trying to build endurance. He's trying not to build lactic acid too quickly. So he's going to go at a slower pace so we can have time for that oxygen to work through, have time for us to get rid of that pyruvic acid. So here's this little stick. I love this little guy because after about a minute 20, he's about to pass out on the sidelines over there. It's like it's my hero. So about first 15, 20 seconds, we are utilizing the ATP that is just sitting in our cytoplasm. The creatine phosphate is just sitting in our cytoplasm. About, again, 15, 20 seconds in, we start to run low on those cytoplasmic stores, and we need to start breaking down sugars in order to replenish and get more ATP floating around. So here we are kicking into glycolysis or anaerobic phosphorylation. And that's going to be good until closer to about a minute 15. And then we're building up our pyruvic acid that runs the risk of fatigue and tiring and lactic acid buildup. So now we need to breathe, get rid of any oxygen debt we might have acquired, because the sooner you get rid of your debt, the better it is for you, right? Right, it's better to pay off your credit card debt early instead of waiting years, because then it just builds up so much money. So we start breathing a little bit more. And even if we stopped exercising, we will have an increased rate of breathing for a few moments so we can clear out any kind of lactic acid that might have built up, go through and work through that pyruvic acid, and then get back to the relaxed state. Okay. Any questions about that? All right. So switching gears. We need to work on our different types of muscle contractions because there's different types of muscle contractions based on what you want your body to do. The first one is tonic contractions. When you have tonic contractions, you have muscle tone. That's what muscle tone is. By definition, tonic contractions are continual partial contractions produced by simultaneous contraction of a small number of motor units, followed by the relaxation of those fibers and the contraction of a different group of motor units. This is why a lot of scientists don't write books, because nobody would want to read that. Okay, so tonic contractions work like Christmas tree lights. We've all seen Christmas tree lights. Mm-hmm. Yeah, because if you haven't, sadness. Okay, when you've got Christmas tree lights, there's two types, right? The ones that are always on, and then the ones that blink. Now, we might have noticed the ones that are always on burn out quicker because the light bulb never turns off. Just like if you have a house light on that's always on, you go through the bulbs faster. If you have blinking lights, even though we say the Christmas tree lights are on, not every single bulb is on at that moment, right? Some are off, some are on. They chase each other. It looks all pretty and fun looking. Yes, blinky lights. If you take care of your blinky lights, they can last forever. I've got some 18-year-old blinky lights. It's like, I'm too cheap to buy new ones. But they're still working because not all the bulbs are on at the same time continuously. They go off and they go on. That's what muscle tone is. You've got a muscle, whether it's your latissimus dorsi, your biceps brachii, any of those muscles, you will have some of the motor units, some of the muscle cells will contract, and everybody else is relaxed. And then those guys will relax and somebody else will contract. And then those guys will relax and somebody else will contract. So just like the Christmas tree lights are on, even though every bulb isn't burning, same thing is the muscle is on, the muscle is contracting, even though not every single muscle cell is contracting at that moment. So that's going to give us our muscle tone, just enough contraction to give us firmness to help keep us upright. So muscle tone is a characteristic of an awake individual. So if you've ever been around people that are asleep, they don't usually have muscle tone. And the best example is if you have small children who have fallen asleep in the living room and you have to carry them to their bedroom. They're all kind of weird and floppy and loose. We're floppy children. They don't have muscle tone. Without muscle tone, there's nothing to keep us together. So you tend to flop and slouch and so on and so forth, like a stack of potatoes. Makes it harder to carry somebody because they're not helping you carry them. They're just floppy. They're not going to have any muscle tone. They're not having any muscle contractions. That's actually a safety mechanism because you don't want to act out your dream of being Muhammad Ali while you're dreaming because you could beat up somebody. And so there are certain times where your brain completely shuts down the body so the body can't move. So there are certain stages of sleep where there is no movement. And that leads to issues like sleep paralysis and things like that. We'll get to when we get to the brain, when we talk about the brain controlling your body and sleep and all that kind of fun stuff. So when you lose consciousness, you will lose muscle tone. So when somebody faints, again, what they tell you to prevent you from fainting is don't lock your knees. Because when you lock your knees, the blood doesn't return from your feet to your body. And if the body doesn't get the blood, that means the blood doesn't get pumped to the brain. If the brain doesn't get blood going to it with oxygen, the brain goes to sleep without oxygen. And of course, when it goes to sleep, it shuts down all the muscles. So you lose all muscle tone, you drop like a rock, you faint, you become horizontal because now you're on the ground. The blood is able to get back to the core of the body, back to your head, and you're able to wake up. So that's what happens when you faint, is your brain has shut off, just like when you turn the lights off on your Christmas tree, and there's no more light present. There's no more muscle contraction. Now, some terms and issues that could happen. Hypotonia, this is less than normal muscle tone. So we often see this with people who have had some kind of brain damage, some kind of health concern, and their muscles aren't able to maintain proper muscle tone, so they can't hold themselves up. They have to have something to support their body for them, like a wheelchair. Hypertonia, more tone than normal. This can lead to spasticity. So they overcontract, so they look very rigid, very robotic. It's like over-exaggerated because their muscles are over-contracting. Too many of the blinky lights are on. So it can cause issues that way. Isometric versus isotonic. So these are kind of evil. They begin the same way. So you have to read the entire word, not just the first three letters, because they both begin with iso. Now, the nice thing is they are direct opposites of each other. So if you know what one is, the other one is exactly the opposite. So our first one is isometric. Isometric, the muscle length remains the same, but the tension increases. So you can feel a tension within your muscles, but you don't see any kind of movement. So if you go to try to pick up your car outside, you can feel your muscles straining to pick up your car, but your car isn't moving. Okay, that's isometric. You are contracting, you are trying, it's just not going anywhere. We also use isometric to do things like if you want to flex your biceps to show everybody your gun show, right? You want to make it look all nice and big. You cause them to tense, but there is no movement. No one's like vibrating their arm while they're showing you because that'd be weird. They're just tensing up everything, even though there's no movement present. Isotonic, the complete opposite. Here, the muscle shortens, so we do have movement, but the tension remains the same. So when you go to pick up something like your pencil, you don't strain to pick up your pencil, right? No one's like, oh, it's so heavy, right? Because pencils are pretty lightweight. So you pick that up, you don't have any tension in your muscles, but you obviously do have movement. So one is tension, no movement. The other one is movement, no tension. A twitch is just a quick, jerky contraction in response to a single stimulus. So a neuron fires and the muscle contracts really quick in response to that. Usually it's mildly annoying, but it doesn't cause any health issues. It's usually not constructive enough to move a whole lot other than just to see the big visible jump and then nothing after that. Tetanic contractions, not to be confused with Titanic. So if you try to type your notes in Word, it always wants to make it a big boat. It's not, it's tetanic with an E. Also not to be confused with the tetanus bacteria. The tetanus bacteria, it produces a toxin that causes extreme complete tetanus. So it causes lockjaw. You can't relax. Everything contracts and then you won't be able to move. You won't be able to relax, and it can be fatal because if you can't move, you can't breathe, and that can be a bad thing. So the tetanus bacteria causes these type of contractions, but these are normal contractions that we're going to have if we can control them properly. So this is just a series of rapid succession where the stimuli just fires and fires so we can keep our muscle contracting instead of lifting and dropping. And we have two types. We have complete and incomplete. Incomplete, the muscle can partially relax between contractions. Now, this isn't always full contraction. It's not like we've lifted and completely dropped and lifted and completely dropped, but the muscles themselves let go a little bit and just enough so they can contract again and relax a little. Okay, kind of gives them a little bit of a break. Complete tectonic contractions, we don't have any kind of break, not even a partial one. So they're continuously contracting the entire time. Your complete tectonic contractions lead to fatigue faster and muscle failure faster because they don't give the muscles a tiny break. Examples of tectonic contraction, when you go and pick up your groceries, right? You're lifting your 50-pound bags of dog food to haul into your house. You don't lift and drop all the way in, right? You hold it. Okay. While you're holding that 50-pound bag of dog food or your, however many bags you can put on your hands at once, you're holding those up. You're not putting those down. The muscles are contracting the entire time so you can hold those things up. So your tectonic contractions allow you to carry the weight. Other than just lift and drop, you can carry from one location to the other. And of course, if you carry for too long, your arms get tired. So here we have our incomplete. So they get a little bit of a break. Even a microscopic moment of break is better than nothing, right? A 5-minute break a couple of times a day is better than not having a break at all. Okay, so we can get a little bit of a rest here. With your complete, there is no break, no relaxing whatsoever. They tend to fatigue very rapidly, and then you can have loss of muscle contraction. So this is something that you may have experienced if you ever had to do wall squats for punishment. Anybody in school used to do that kind of crap? And you sit on the wall, they're like, stay. And until your thighs quiver and fall, and then you lean over and you're like, I can't move anymore. Sad turtle looks, right? Okay. We used to have one chick or one teacher. She favored dictionary punishment. So you do something naughty, you had a dictionary in each hand and you had to hold it up. And if you dropped, you had detention. So if you did something naughty at the end of class period, you might be able to tough it out. But if you did something naughty at the beginning of the hour, you're like, I'm going to have to. A lot of people are like, you know what? I got it. Give it to me, because they didn't want to go and get tired. So if you carry something heavy for too long, fatigue is going to set in and you'll end up having to drop the weight because you just can't carry it anymore. TREP. A series of increasingly stronger contractions in response to a constant stimulus. So the nerve impulse, the stimulus, doesn't change. It's constant and doing the same firing at the same rate. But the reaction of the muscle is stronger and stronger each time. It's kind of like if you have one of those days and your kid just really gets on your nerves. They're not doing anything abnormal. It's just the basic constant, hey, what are we doing? What's for dinner? Are we there yet? Eventually you're going to snap. It's okay to admit it every now and then we get to those moments and I need to be alone for a moment for your safety. Okay, so that's what TREP is. Each time that nerve fires, even though that nerve isn't firing any faster, that nerve isn't firing any stronger, the muscle is going to have a stronger and stronger and stronger reaction to it. And that's going to be for the first about 30 to 50 reps of that muscle contracting, and then it balances out. We've reached our peak and optimal level of working. And that's the job of TREP, is to warm the muscle up, preparing it to do work. So again, when you go exercise, you don't fall out of your car and immediately start bench pressing 100 pounds, right? You work your way up to that. If you're going to go running, you don't just fall out and sprint, right? You're going to stretch a little bit. You're going to walk around. You're going to get those muscles going and moving, and then you're going to engage with those guys. That way you don't injure yourself. So it helps prepare the body to work the best that it can, most efficient way that it can, without causing damage or issues. So one of the reasons why they tell you to warm up before you do a lot of physical activity. Fatigue and contracture. These two things have the exact same cause. They just happen at different times. So as we learned last week with sliding filament theory, it takes ATP for myosin to grab onto actin and yank, and it takes ATP for myosin to let go. So depending on, do we run out of ATP before we grab, or do we run out of ATP after we've grabbed? We'll have one or the other of these issues. So fatigue, failure of a muscle to contract in response to repeated stimulus due to lessened irritability or contractility. So it's kind of like you have a lazy dog and you like, move, move, and they just lay there and look at you. No matter how many times you yell at them, they're just going to lay there and look at you. That's your fatigue. You're telling the muscle you need to contract, but they don't have any ATP. And if they don't have any ATP, they can't grab onto actin and yank. So it doesn't matter how ready they are, you're not going to be able to have that muscle contraction. So ATP production fails to keep up with the demands, fatigue sets in, muscle activity stops even if you're stimulating. Now again, most of us very rarely hit fatigue unless you got punished a lot with the wall squats. Most of the time our brain stops before our body does because our brain's like, no, I'm done, versus the body who could keep going. Okay. This is actually why zombies are stronger than people. If you've ever wondered how come every single zombie movie, the zombies are superhuman strength.
Mm-hmm.
Right? How can they bite through that person? How can they rip open that person's chest cavity? Or how can they rip off that limb? You can too, except your brain says, you know what? You shouldn't bite through that because you'll hurt your teeth. Okay? You shouldn't try to rip open somebody's rib cage. It's rude and you could break a nail. Your brain stops your body from doing a whole lot of stuff that it can do. So you do actually have the ability to do everything the zombies do. You just have to figure out how to turn your brain off so your brain will stop going, you can't do that.
Is that similar to like gorillas, how they use a larger percent of their muscle than humans?
In part.
Okay.
That and their muscles are much bigger. Or myofibrils, bigger contractions. But yeah, our brain says, not today. And then your body's like, okay, I can do it. So very few of us actually fully get fatigued. Okay. If you want to see true fatigue, watch the end of a marathon because it's pretty boring other than that. But a lot of times those runners will come in and collapse and they have to drag them out of the way because they just don't have the energy to move anymore. Then they wrap them up like a burrito and give them some food and water and hope for the best. It's because they've run out of energy. They can't go anymore. Contracture, same problem. We've run out of ATP, but instead of running out on the grab, we ran out on the let go. So if we don't have enough ATP to let go, myosin can't release actin, you're not going to be able to relax. So instead of fatigue, can't contract because you run out of energy, contracture, you can't relax because you run out of energy. So incomplete relaxation after repeated stimulus. So you stay contracted because you've run out of ATP and the cross bridges do not detach.
Is that a cramp?
We'll get to what a crampity cramp is, but this would be rider's cramp. So if you've had full-on rider's cramp, your hand's stuck, okay, and it's like, I can't move it, it hurts. Most of us rub, okay? And that's because instinctually we know if we rub, it increases blood flow, more oxygen, more ATP production, alleviate lactic acid. We might be able to move a little bit better. Okay, so we increase blood flow, it's going to help us out a whole bunch. So that's why when some people get contractures, they just rub. It's because it increases blood flow. It's going to help with that. Now, some people will get those really wicked leg cramps. They're not really leg cramps, but their muscle contracts and doesn't relax, and they have to just kind of force their way to make their muscle relax. You'll see that sometimes in people's calves. Those are contractures. We're not able to relax with some of those guys. Now, all of these muscle contractions we've talked about, tetanus and TREP, and even fatigue and contracture, are normal. They happen. We may not like fatigue, we may not like contracture, but it is something that cells can experience even at the tiny level at some point in time. Now, abnormals, there's an issue there. Okay, so with a convulsion, abnormal, uncoordinated tectonic contractions of varying muscle groups. We just don't relax like we're supposed to, contract like we're supposed to, not in unison, so it's kind of chaotic. Everybody's kind of for themselves, so it's going to cause those convulsions. A fibrillation, this is where an individual muscle does not contract with the rest of the group. So within our muscle fascicles, you have one muscle contract while everybody else is relaxed. It's kind of like listening to music, and if somebody plays on the third beat instead of the fourth beat, you hear it's like, well, that's wrong. That's what happens with that fibrillation. Now with fibrillation, since it's an individual muscle cell contracting differently than everybody else, one cell isn't enough to move your whole body. So you can't see it. There's no constructive movement, but you can often feel it. You feel like your muscles are fluttering. So we see this sometimes in your eyes, especially because eyes do not have any slow fibers. They have fast fibers, and then if they overcontract, they have issues. So if you've ever had one of those moments where it feels like your eye's pulsating, you're like, hey, is my eye twitching? And they're like, no, why are you staring at me all weird? I feel like my eyes are twitching. you might have a fibrillation in one of those muscles. You can feel it, but you're not having any kind of movement because it's not big enough to move those structures. Now, with fibrillation in skeletal muscles, it's weird. It's not right, but it's not going to kill you. It just is, it might be mildly annoying until your muscle decides to play like the rest of the guys are supposed to play. Now, in the heart, fibrillation can be fatal, right? You go into VFib, your heart muscle isn't contracting like it's supposed to, you can die quite quickly. Atrial fibrillation, it takes a little bit longer because atria are smaller, so their effects are not as potent as VFibs. Okay, obviously we know VFib goes into cardiac arrest quite quickly. Rigor mortis, a state of contracture of all muscles of the body after death. And I know you're super excited. You're thinking, oh, I just have to look for the word death and I got this. I don't have to put the word death. I can put a state of contracture of all muscles in the body due to leaking calcium. Okay, so don't look for just death. Okay, so what happens? When you die, your body breaks down. Duh, right? It's called rotting. Okay, it happens, decomposition. When we look at it, squishy structures in the cells break down faster. So in our muscle cells, skeletal muscle cells, the sarcoplasmic reticulum is basically a water balloon filled with calcium. So when you die, it breaks down fairly quickly. And when it releases calcium, we learned last week, calcium is that final trigger of muscle contraction. Once it binds to troponin, it will twist and change the shape of troponin, which will move tropomyosin from the bonding site. And as long as there's ATP, myosin will grab onto actin. It can't say no. So that's how rigor mortis happens, is you're going to have that myosin crawling along that actin until it runs out of ATP and can't let go. So it has contracture. It has that muscle contraction that won't relax. For the average person, it's going to begin about 3 to 4 hours after death. It takes a while to stuff rot and float and all that kind of fun stuff. Peak rigidity is roughly 12 hours in and will dissipate over the next 48 to 60 hours. The dissipation is not the muscle relaxing. We're not coming out of contracture because we let go. It's because the myosin and actin are goo, and goo cannot grab goo because it's goo. Okay, so your cells are liquefied by this time, so there's nothing to maintain firmness in your body. Now, they used to use this to determine time of death, but then we realize stuff happens. If it gets cold, things do not decay as quickly, so you go into rigor slower, you come out of rigor slower, which is why they put you in cold storage whenever you die to try to slow down rigor mortis so, they can make you look good in a box. If it's hot, things rot quicker, so it's going to speed up. So if you crank the AC, it'll be longer before the body smells and anybody notices. If you crank the heater, they're going to notice real fast, but it's totally going to mess up timelines. This is one of the reasons why nowadays they do liver temps, because regardless of ambient temperature, what's going on in the body or in the air around the body, liver cools off at a fairly constant rate regardless of temperature. So that's why that's used more often until you reach the temperature of the room. And then after that, you just hope for the best and put together all the clues you can to figure out time of death. Spasm versus cramp. So again, these are some of the most misused terms out there, kind of like we say wristwatch, even though we all have learned it's on your forearm and not your wrist. So a spasm, a forceful, painful contraction of a muscle due to a chemical imbalance. So if you have somebody and they're like, oh my gosh, I had this really bad muscle cramp and then I ate, a banana and it got better, or I drank pickle juice and it got better. They didn't have a cramp, they had a spasm. Okay, so if you can eat something and it gets better, and that something is usually sodium, that's what the pickle juice is, or potassium, that's what the banana is, or even calcium. Drink a glass of milk. That is going to change the electrolytes in the system that will allow that muscle to function like it's supposed to. It can also be caused by toxins. Okay, so if you take a pill and it starts twitching, that could be causing a spasm, or you take some kind of poison, or you absorb something from the environment, that kind of scenario. A cramp, painful tectonic contraction similar to a spasm, but the cause is different. So if you were to have a cramp followed by a spasm, they feel exactly the same. The difference is what caused it. With a cramp, you have cyclic impulses from the nervous system. So it's caused by a nerve misfiring instead of just a change in ions, just a change in chemistry. So we've heard a lot of people say things like, oh, I pinched a nerve and now I have back spasms. But if you pinched a nerve, now you have back cramps. Because it's the nerve misfiring that is causing your muscles to overcontract or undercontract. So if it's a nerve problem, it's a cramp. If it's an electrolyte imbalance, it's a toxin, then it's going to be a spasm. Same results, same pain, same issues, but it's going to have different causes to it. So what alters strength? Because we know not all muscle contractions are the same, right? You don't use the same effort to pick up your pencil as you do to pick up your backpack. So we're going to have different levels of strength intensities with our muscle contractions. The first one is that initial length. So as we learned last week, as the muscle contracts, the myosin is going to pull the actin towards the center of the A band, and the I band, the H zones, they all disappear until the Z lines come in contact and our muscle contraction is done for that sarcomere. And of course, it spreads to adjacent sarcomeres. So what happens is, if we take the sarcomere where the Z lines are anchored, if we spread the Z lines out a little bit, it takes longer for them to come back together, takes longer for them to touch. We can generate a greater muscle contraction. So the more stretched the muscle is before you contract, the stronger that muscle will be able to contract in the end. Now, again, this is why we take advantage of warm-ups, okay? So we are able to work our way up to those optimal levels by stretching our muscles so they can contract more efficiently, they can contract stronger. Now, weight of the load, this increases. The heavier the thing is, the bigger the muscle contraction has to be, right? Picking up your pencil, you're going to need a stronger muscle contraction to pick up your backpack, and you're going to need a bigger muscle contraction to pick up your groceries, that kind of scenario. The reason why you have to have more contraction when the weight is heavier, that weight slightly stretches your muscle. When you go to pick up something heavy, imagine if you're picking up something super heavy, you first feel that strain. That strain does, at the microscopic level, stretch you a little bit. And since it stretched you, you're going to generate greater contraction so you can pick up that heavier thing. So the heavier something is, the more it stretches you. The more it increases that initial length. So it does the warm up for you. It does the stretch for you. Again, up to maximum. Obviously, you can't work your way up to car in one day. You're going to have to do it a little at a time to get to the point that you can generate those muscle contractions strong enough to move something super heavy. Satisfactory metabolic conditions. This is kind of duh, right? If you have enough oxygen, you have enough nutrients, everything's healthy and happy and functioning, you're going to do better than if you don't have oxygen, you don't have nutrients, you have lactic acid buildup, you have tears to the muscle, just like your life, right? If you're happy and you sleep well and you have a full belly, you do better during the day than if you're hungry and you're tired and you're cold and you're cranky. Okay, so happy muscles, happy conditions for them to work. Strength of the stimulus. A weak stimulus, just a few neurotransmitters, gives you a weak contraction. A strong stimulus, more neurotransmitters, gives you a bigger contraction. Kind of like the difference between if somebody taps you on the shoulder, you might turn and say hello. If somebody slaps the back of your head, you're going to do more than just turn around and say hello. Right? Bigger reaction because of a bigger stimulus. Don't slap people. Rate of stimulation. So the faster we stimulate, the more neurotransmitters and the quicker succession those neurotransmitters are released, the stronger the contraction. Again, if your kid says, I'm hungry once every 10 minutes, it's mildly annoying. But if they say, I'm hungry once every 1 minute, you're like, oh my gosh, just eat some freaking cookies and leave me alone. So the more we stimulate, the stronger that muscle is going to contract. The fluid of the temperature of the fluid around the muscle. If we warm up that muscle, latent period becomes shorter, height of contraction becomes greater, relaxation, it becomes faster because, again, it takes energy to contract, but then it takes energy to relax. And if you can contract faster and relax faster, you're going to build up greater strength, greater endurance, and your muscle's going to work faster. Again, this is why we warm up. So we warm up to take advantage of TREP, getting us up to those optimal working levels. We warm up to take advantage of stretching the muscle so we can contract more strongly each contraction, and we take advantage of warming up to warm up the area so we can transport nutrients faster and oxygen faster and get the job done faster. So warm-ups have valid science reason to do. Hypertrophy versus atrophy. So these are terminologies. Hypertrophy, more than normal muscle tone, bigger muscles essentially, and we know bigger muscles are stronger muscles, right? Right, we look at somebody built like Arnold Schwarzenegger, especially in the 70s, you're like, I bet he's strong. Right? You don't look at him going, I could take him. I'm sure he's all Ripley, but he's a wuss. Yeah. Big muscles, big strength. Atrophy, when your muscles get smaller, they shrink. Smaller muscles, less contraction. Okay, right? The little skinny guy, we don't expect him to be very strong. because he doesn't have a big muscle mass. He doesn't have the ability to generate a lot of contraction force. Questions about skeletal muscle? All right, cardiac muscle. Just a little blurb about cardiac muscle, because again, you're going to see it in A&P2. There's a whole chapter. But they do share a lot of similarities with our skeletal muscle that allows them to function similar to our skeletal muscle. Now, they are uninucleated typically, and these cells are going to be a little bit smaller than your skeletal muscle, but they're still striated. They still have A bands and I bands, which means we still have those same structures of muscle contraction with skeletal that we do with cardiac, with the myosin grabbing, actin, and pulling, and getting those Z lines closer and closer together within the skeletal muscle. They're going to have intercalated discs, those gap junctions and desmosomes that attach the muscle cells together. So that way, no matter how hard they pump, they don't fall apart on you, so they don't shred like chicken meat or something. And because of the intercalated discs, the cells all interlock. So mechanically, chemically, they're all connected. So you only have to send neurotransmitters to one cell before it spreads throughout the entire muscle, or I'll send electrical impulse from one cell and it spreads throughout the entire muscle. So much more efficient, since we don't have to go to every single muscle to stimulate it like we do skeletal muscle. This is also why sometimes it's hard to pick out individual heart muscle cells, because they do intertwine with each other. Now, our heart muscles exhibit something called automysticity. Sometimes you'll see it called autorhythmicity. They're interchangeable. This means that they can contract without neural stimulation. Okay? We have what we call a myogenic heart. The heart can work without the brain, which is why a chicken can run around like without a head, like a chicken running around without its head. It doesn't have to have the brain to tell it to contract. That chicken will keep running until it runs out of oxygen or runs out of blood for the heart to pump. And so the heart just keeps on going until it runs out of that energy, because it has its own pacemaker cells that generate their own electrical impulses to stimulate the muscle cells so we can coordinate and have muscle contraction. Smooth muscle. So we're going to spend the bulk of our time comparing smooth muscle to to skeletal muscle, how they're different, and how those differences affect functionality. And that's because these two, smooth muscle looks very different than our skeletal muscle, our cardiac muscle, because it functions very different than our skeletal muscle and cardiac muscle. Now, these are the smallest of the muscle cells. They are spindle-shaped, fat in the middle, tapered to the end, with one nucleus in the fat part. They are involuntary. We can't control them. They're going to be located in our hollow organs of the digestive, respiratory, urinary, reproductive systems, blood vessels. Now, instead of having fascicles, those bundles that contract together to generate contraction forces in skeletal muscle, they're not going to have that. You don't shred menudo like you shred pork, right? Right. If you have menudo that has shreds, somebody threw a tongue or pig feet or something weird in it. That's skeletal based. Okay, so if it's just digestive organ, it's not going to shred, because the cells don't have fascicles to shred and fall apart. They're aligned in sheets. Okay, so they all work as one big blanket. And we have two. We have the circular layer and the longitudinal layer. They run perpendicular to each other. When the circular layer contracts, it's going to constrict the lumen, make the space smaller in the organ, causing that organ to elongate. The longitudinal layer does the opposite. It's going to cause the muscle to shorten. So we get this alternating lengthening and shortening of the organ. And when we lengthen and shorten, it causes a squeezing motion, just like squeezing ketchup to mix it up and then pushing it out through the hole in the ketchup bag. Right? We've all done the ketchup thing. Mix the ketchup, because you don't want ketchup water and ketchup separated. It's weird. And then you squeeze it out the hole. Same principle. You're doing alternating squeezies, and that is called peristalsis. So our skeletal muscle pulls because of the way the muscle cells are arranged, the fascicles are arranged. Our cardiac muscle pumps because the way the cells are arranged. They don't have fascicles, so again, you don't shred heart like you shred pork. And our smooth muscle doesn't shred either, because there's no fascicles. They're arranged in sheets that are going to contract in opposing groups so they can do peristalsis. So the anatomy of smooth muscle. They do have endomysium, right? The connective tissue around the outside of the muscle cell. They do have that, but they don't have anything else. They don't have perimycin because they don't have fascicles, bundles of muscle cells. They don't have epimycin. They don't have deep fascia. They don't have superficial fascia. So it's one of the reasons why, again, when you cook your smooth muscle, it doesn't fall apart as easily as skeletal muscle after it's been cooked a long time because it doesn't have all those connective tissues holding it together. It just has that endomysium. They are arranged in sheets that contract together instead of being in fascicles or bundles. There's no striations. There's no A bands. There's no I bands. There's no Z lines. Labeling these guys would be so much easier than, what we just got done doing in lab today because they don't have any of those structures associated with them. They don't have sarcomeres because we learned the sarcomeres, Z9 to Z9, is the basic functional contractile unit of skeletal muscle. We don't have a sarcomere in your smooth muscle. And in a cardiac muscle, there's a little bit different arrangement that gives it a little bit more play, a little bit more energy boost when it comes to contraction. We still have thick and thin myofilaments. We still have myosin and actin because anything that moves, whether it's a muscle, smooth, skeletal, cardiac, or even if it's the flagella or the pseudopodia of a bacteria or anywhere in between, if we have movement in a cell, it's always actin and myosin do it. Those are the moving proteins across all living things on the planet. So we still have thick and thin myofilaments. We still have actin and myosin, but they're arranged differently. In smooth muscle, myosin is bigger. And being bigger myosin means more grabbing action, which means more contractility. So smooth muscle, we're going to find, is very well adapted for being powerful and still being tiny. So everything a smooth muscle cell can do is just like what a skeletal muscle cell can do, but the skeletal muscle cell is like 5 or 6 times the size. Okay, so these are small and mighty little efficient guys. The neuromuscular junction. So again, when we talked about the neuromuscular junction in skeletal muscle, that neuron doesn't talk to the entire muscle, right? It parks at the motor end plate, right? The area. Oh. Okay. So the motor end plate of our skeletal muscle, like the driveway where you park your car. So we don't release neurotransmitters all over that muscle cell. We just go to this one section and we hover right above it so we can release neurotransmitters so they can be sucked up within the muscle cell as quickly as possible so we can contract as quickly as possible. So that shortens excitation, contraction, coupling, and enables the ability to contract efficiently. With smooth muscle is like having 140 acres when you're a farmer. There is no driveway. You can go wherever you want and park wherever you want as long as you have a truck. Okay? That's how smooth muscles are. They don't have a driveway. They don't have a motor end plate that has the subneuroclefts or junctional folds to suck in neurotransmitters. The entire cell can receive neurotransmitters instead of just one little place that parks. So when we have the neuromuscular junction of the smooth muscle, it's often referred to as a diffuse junction because it talks to the entire muscle cell, which is able to do because it's so small, and any part of that muscle cell can receive those neurotransmitters. So we release it into a very wide synaptic cleft, and it drifts down and gets picked up by the muscle cell based on diffusion rates. So it's the difference between UPS delivering a package to your house by parking in your driveway and walking it to your porch versus if UPS did airdrops and just went over the zone and just dropped. It'll get there eventually once the parachute opens and it floats down and you hope nobody else gets your package. Okay, so these guys are like airdrops. It takes longer for that neuromuscular junction to communicate. And again, that's why they're sometimes called the diffuse junction, because it takes so long for that neurotransmitter to diffuse across the space. The sarcoplasmic reticulum, again, in skeletal muscle, it is a crucial player in muscle contraction. It stores calcium, and when it's time to contract, it will release calcium, that final trigger for contraction, so we can have that muscle contraction. In smooth muscle, it doesn't store calcium anymore. It's kind of like, getting bumped down from the head cook down to the dishwasher. So the sarcoplasmic reticulum no longer plays a role in muscle contraction. It no longer stores calcium. It just does what other endoplasmic reticuli do. So it has a different setup. Our T-tubules, those doorways into our muscle cell, the blue guys, we have those in skeletal muscle so we can bring in the urge to contract very quickly. With smooth muscle, they don't have T-tubules. They don't have those doorways coming in. They don't have triads because they don't have T-tubules and the relationship with the sarcoplasmic reticulum. Instead, they have something called caveoli, which is like ravioli, but instead of little pockets of meat that's delicious, it's little pockets of calcium. Okay, so remember ravioli, caveoli, little pockets of something, and calf because it has calcium in it. So again, our skeletal muscle, when we look at the cell membrane, we've got all those T-tubules across its surface with the sarcoplasmic reticulum on either side. So when it's time to contract, that action potential travels down, comes in at the T-tubule, stimulating the sarcoplasmic reticulum to release its calcium, that final trigger for muscle contraction. And it's going to travel down and go into all the T-tubules, releasing all the calcium stores so we can flood full of calcium. Now with smooth muscle, we do not have T-tubules. We do not have sarcoplasmic reticulum playing any role in muscle contraction, so no triads. Instead, even though it's called smooth muscle, it's actually very wrinkly. At the cell membrane level, they've got all these little patches in the cell membrane. And these little patches are called caveoli. And they're going to store calcium on the outside of the muscle cell. Okay. Now, calcium is still the final trigger for muscle contraction. The difference is, in order for us to bring it in for that contraction, we have to open calcium channels so calcium can come in. So as we talked about last week, this is why if you want to lower your heart rate or your blood pressure, you can take a calcium channel blocker that keeps the calcium outside instead of inside. It'll cause smooth muscle relaxing, lowering your blood pressure. Now with your heart muscle, it's almost like these two are blended together. So the heart muscle still stores calcium in a sarcoplasmic reticulum to help with our contraction, but it also keeps calcium on the outside and has calcium channels to bring stuff in. So your heart muscle does a combination of the stored calcium to use as well as bringing excess calcium to use. So calcium channel blockers not only lower your blood pressure because it relaxes your smooth muscles, but it will also lower your blood pressure because it partially relaxes the the cardiac muscle. It doesn't do it completely because if your heart completely relaxed, well, it'd be very relaxing because you wouldn't wake up. So we're just going to dampen that muscle contraction by having calcium channel blockers. So this is why we have rigor mortis and skeletal. When we die, these start leaking and calcium comes in and causes that muscle contraction. With smooth muscles, since there's calcium stored on the outside, the only way to have it leak inside is to break down the cell membrane. And by that time, it's already mush. It's not going to contract. So this is why about 30 minutes to an hour after you die, your smooth muscle all completely relaxes. So you'll wet your pants if you've got pee or urine in your bladder. You'll poop if you got poop in your rectum. So a lot of times when somebody dies in the hospital, they just don't leave them there for a while. They're going to get them out of the room as quickly as possible because they don't want them to release while they're still in the room because that's a mess to have to clean up, and nobody wants a dead person pooping next to you. It's a little, get it out. But this is why you don't rigor mortis in your smooth muscle, but you do in your skeletal. It's all where the calcium is stored. Completely different setup. And different medications to control either one. Not the death part, but the functioning part. So calcium channel blockers would not work on skeletal muscle because they store all theirs on the inside, which is why it doesn't cause paralysis while it slows down your heart rate and your blood pressure. So here's showing you that varicosity. It's kind of like little bubbles, almost like if you unwound a balloon poodle. So they're just hanging out above the sheet of smooth muscle, and they'll release that neurotransmitter into this very wide, diffuse junction. And it's going to rain down over all of it, just like air drops from an airplane. And it'll eventually get to where it's going and land and stimulate that muscle cell. The thick myofilaments, the myosin, have actin gripping heads along their entire length. So if you remember last week when we looked at our picture of skeletal muscle, the H zone doesn't have actin. So the H zone, the myosin doesn't have those little gripping heads. So that one picture, it showed that it was a bare area or bare zone. because there's no gripping heads, because why have heads to grab actin if there's no actin to grab? Now with smooth muscle, there is no H zone. There is going to be the opportunity to grab actin along the entire length of that myosin. So not only is that myosin bigger so it can grab harder, but it can grab its entire length, generating a stronger contraction, more efficient contraction compared to skeletal muscle. The thin filaments, they do have tropomyosin, but they do not have troponin. So again, troponin is that regulatory protein. So as long as troponin is not touching any calcium, everybody stays in place. Again, when it's time to contract, calcium binds to troponin, twisting, changing the shape of troponin, moving tropomyosin from the binding site, and actin can be grabbed upon by myosin. With our smooth muscle, no troponin. It's the difference from living at home, so you have a curfew and you have to ask permission to do stuff, and you wouldn't do things under your parents' roof that you would do under your own roof kind of scenarios. But when you move out, there's no more curfew. You know, I can leave at 4 a.m. if I want to. Why? I don't know. Want to see darkness, right? You can party whenever you want to. You can do whatever you want because there's no more regulating you when you're an adult and you live in your own home, right? I can eat chocolate cake for dinner if I want to. Neener. It don't matter because there's no regulatory. Now, there is some regulation when you move out because usually you have a landlord that will tell you if your radio's too loud, okay? Or the cops will come over if your radio's too loud. So there is regulation, but not as much regulation as living with your parents. So smooth muscle has some regulation, but not as much as skeletal, because skeletal's got that lockdown situation with troponin and tropomyosin. The thin and thick myofilaments are arranged differently. So again, in skeletal muscle, they're sliding past each other. So they're just lined up next to each other. With your smooth muscle, they're on a bias. And when they contract, they scrunch. They kind of twist around each other like a corkscrew. And scrunching generates more force than just pulling, right? And you can, reenact this. When you wad up a piece of paper, it feels more satisfying, like you did more work than if you just folded a piece of paper. Okay, so scrunching is going to generate a lot more force, allowing you to be more efficient. Intermediate filaments. These are longitudinal bundles of non-contractile cellular components of proteins, and they are there to help resist tension. So these little guys make sure that no matter how hard your smooth muscle scrunches, it doesn't shift position. So again, when you wad up a piece of paper, it doesn't matter how much you wad it up or how much you beat it together. If you were to unwad it, it's still a square piece of paper. It's not like you can do this so much that it comes out triangle, right? It always goes back to the original shape because the fibers of the paper maintain the integrity of the paper. That's what these intermediate filaments do. They maintain the integrity. Now the dense bodies. The dense bodies will attach to the thin myofilaments, okay? So they're going to anchor the actin in place. In that regard, they're just like Z-lines. So skeletal muscle has Z-lines to anchor actin. Your smooth muscle has dense bodies to anchor actin. So again, no matter how hard we pull on actin, we can't unravel. The difference is in smooth muscle, the dense bodies not only hold actin in place, but they tack it down to the sarcolemma, the cell membrane, and they attach it to the intermediate filaments. So we have everybody attached and anchored to this dense body. With the skeletal muscle, that Z-line is just on that myofibril. We don't connect myofibrils together. We don't connect muscle fibers together, nothing. Everybody works independently. Where smooth muscle, everybody's attached. And that helps to harness the contraction force more efficiently. Your skeletal muscle would be like if you had your horses pulling your cart and only 3 of them were hooked up to the carriage and the other horses were just running around for moral support. Okay, they're not helping you pull the carriage because they're not attached to the carriage. With smooth muscle, everybody's attached to the carriage. So there is no moral support. Everybody's hooked up so we can harness more efficiently. So everything we see with smooth muscle is to make it way more efficient, make it way stronger. That way we don't have to have as many. We don't have to be as big and still get the job done. So smooth muscle, even though they're tiny, can contract just as much, if not more than skeletal, because they're better at their job. They're more efficient at their job. So that strong intracellular skeleton to harness the contraction. Now, not only are we connecting the actin to the sarcolemma, but we also connect it to the endomysium, the connective tissue. That's not the case with skeletal muscle. With skeletal muscle, It's kind of like your foot in a sock in a boot, okay? Your boot is not fused to your socks, right? Your feet are not fused to your socks. So if you want to move your boot, you really have to wiggle your toes a lot to try to move your sock, and you have to super wiggle to move your sock and your boot. So you waste a lot of energy trying to move the bigger structure. That's how skeletal muscle is. The myofibrils are not attached to each other, and they're not attached to the cell membrane, and the muscle cells are not attached to each other. They're not attached to the other components of the fascicle. They're just loosely bound by, but they're not fused together. Your smooth muscle is kind of like toe socks. Okay, those are still popular. Or occasionally, if you remember, like for that brief year, they had the toe shoes that were going to revolutionize footwear until people realize when that happens, if you bump your toe in toe shoes, there's no protection and you break things. Remember toe shoes? Yeah, they sucked. Basically, they were shoes that looked like toe socks. So, okay, you love those, but your toes are not very well protected. A lot of people sprain toes. And of course, if you have big feet and big toes, really made it uncomfortable to try to find shoes that fit you. But if you wear toe shoes, you wiggle your toes, everybody sees it. Your toes are moving with your shoes and stuff like that. Okay, so again, skeletal muscle, not very efficient because we're not all tied together. With smooth muscle, we are very efficient because we are all tied together. We're in this together. So there's our lovely smooth muscle. So we can see the intermediate filaments. Those guys are just hanging out, creating a skeletal structure. You're going to have the dense bodies that are holding the thin myofilaments. There's your actin. There's your myosin. It's so thick. It's much bigger than it is the skeletal muscle. And we can see that the pink is lined up along the entire length of the myosin. So lots of grabbing opportunity. So we can grab, yank really hard. So we can generate a lot of contraction force. You don't have to stretch before you go to the buffet, right? Right. No one goes, hold on, I got to warm up my stomach. No, it's going to do it because it's very, very efficient. And this is them contracting, scrunching down. Scrunches give us more power. Okay. So with smooth muscle, it is slow and synchronized, right? When you eat, it's not going to instantly pass through, which is great because snack time would be really awkward if you had to poop like 5 seconds after you ate. Creepy. But it takes a while. Very slow, very synchronized. And again, we're doing peristaltic contractions, making it very efficient and very strong. So resistant to fatigue. Nobody goes, oh my gosh, I ate Thanksgiving and I was so exhausted from eating Thanksgiving, I couldn't eat for the next week because my stomach was too tired. No, right? But there are those people like, I went to the gym, I was so tired, I just skipped the rest of the week. It's too much. So these guys don't fatigue like skeletal muscles because they're more efficient. They're built for it. Action potentials can also move from cell to cell with gap junctions. So again, it's not a necessary step to stimulate every individual muscle cell. We can go and stimulate a group, and that group can act as a pacemaker that will send signals to the entire organ. So this is how a lot of the digestive system is. You'll have a patch in the stomach that receives neural impulses, and it spreads throughout the entire stomach, or a small patch in the small intestine that spreads the entire small intestines. Now, as mentioned, calcium is stored outside in those caveoli, which allows high concentrations of calcium available when we need it. When we need to have a stronger contraction, we just open up the calcium channels and it floods in, allowing for muscles to contract. Now, we will have a regulatory protein called calmodulin. Just like, again, you're not living at home, so you have a landlord instead of a parent that regulates you, but it doesn't regulate you as much as a parent would. So calmodulin is still going to dictate contraction, but not as strictly as troponin and tropomyosin. So how they are like, how are they different? So actin and myosin still interact using sliding filament theory. This is the same for everything that moves. Cardiac muscle, skeletal muscle, smooth muscle, bacteria, flagella, all those guys all use myosin and actin in sliding filament theory. The final trigger is always calcium. It doesn't matter, again, which type of muscle we're looking at. Calcium is going to be that final trigger. And we're going to energize this with ATP. Myosin uses ATP to grab and yank, ATP to let go over and over and over. So that's going to be the same across the board. How they are different, as we've talked about, our smooth muscles more efficient with the way it's built. So our calcium interacts with regulatory proteins, calmodulin and myosin light chain kinase versus troponin and tropomyosin. That allows it to respond a little bit more efficiently. The thin filaments lack troponin, so they can contract at a faster rate. There's not that whole step there. Just like if you don't have parents living with you, you can party whenever you want. You don't have to ask permission. You just do it because you're an adult now. Our smooth muscle has something called plasticity. Plasticity is the ability to function over a wide range of lengths. So with our skeletal, we just saw the more stretched, the stronger contraction we can have. So that means when you want to have a strong skeletal muscle contraction, you can contract all the way, but before the next one, you have to completely relax before you contract all the way. Again, this is something you might notice if you go to the gym. Nobody goes and, wiggles at the gym, right? You don't ever see the guys with the big weights going, oh. No, shake weights don't work. They look weird, a little questionable. They don't actually work because in order to have a full push, you have to completely relax after that contraction before you do it again, right? Whenever you are powerlifting, you don't go, right? You got to go all the way, all contracted to all the way relax. You can't vibrate. Smooth muscle doesn't have to do that. They don't have to completely relax. They can wiggle like a shake weight and still be just as strong. So they stayed partially contract all the time. That way, since they're already partially contracted, it doesn't take as much effort for them to work, so they can be faster and they can be stronger compared to that skeletal muscle. So when we look at it as an example, your small intestine in a living person is 10 feet long because it's partially contracted. In a cadaver, it's 21 feet long because it's completely relaxed. When we're digesting, your small intestine doesn't have to go 21-10, 21-10, 21-10 when it's contracting. Because would that not be terrifying, everybody walking around with their bellies pulsating? I would find that terrifying. There goes tight pants, okay? Thanksgiving, everybody would be quivering like crazy. No, we don't have to completely relax to completely contract again to handle those big meals like your skeletal muscle would have to. And if we were so efficient, nothing else is going to stop it. So with skeletal, run out of ATP, can't contract anymore. Oh, we don't have neurotransmitter, can't contract anymore. Don't have calcium, can't contract anymore. Smooth muscle, no ATP, who the hell cares? I'm real efficient, I'll keep going. Don't have neurotransmission, who cares? I'll still keep going. The only way to slow these little buggers down is to reduce their calcium. So they don't have as many weak points as we would find with skeletal muscle. That's why we don't have as much problems with smooth muscle as we do skeletal muscle with their functionality. So smooth muscle, as you figured out by now, has very low energy requirements. So low, they have few mitochondria. They can run basically their entire existence on anaerobic pathways, glycolysis and ATP stores. So they don't need a lot of oxygen. They don't need a lot of mitochondria to keep them going. Now, shifting gears a little bit, how do we control smooth muscle? Since they don't have to have that direct connection to a neuron like a skeletal muscle, they have a little bit more freedom with their functionality. So we have two different types, two different kind of schools of thought with controlling the smooth muscle. We can have multi-unit smooth muscle or visceral smooth muscle. Now, your book uses the term single unit smooth muscle instead of visceral. That way, unit muscle is in there. So multi-unit versus single unit smooth muscle. I use visceral because visceral means organ. So those are the ones your organs use versus the other guys. So multi-unit, these are more like skeletal muscle in their reaction times. They're fast. They have more of a connection to their neuron like skeletal muscle. This allows them to still have those efficiencies that we see with smooth, but have a little bit more speed to them, a little bit faster. So they have motor units like skeletal. They're going to be found in the iris of the eye. So again, when it's bright outside, you want to constrict as quickly as possible so you don't get blinded. Or you walk into a dark room, you want to dilate as quickly as possible so you can see in the dark. Male reproductive system, enough said. Arteries, large arteries. Okay, so if you cut your arm off, the artery will constrict really fast. That way you don't bleed out so quickly. It's going to save your life, hopefully, allowing for other mechanisms to come into play. The erector pili muscles, right? When you get goosebumps, it's not slow, right? No one goes, oh, I feel it. It's starting to happen. Any minute now, that goosebump's going to, oh, there it is. It's the goosebumps. No, you get them really fast because these guys act a little bit more like skeletal on speed. Your visceral smooth muscle, this is the diffuse junctions. We don't have that direct connection, that motor implant, anything like that. So we just allow for those neurotransmitters to get there when they get there, and will respond when it's time. So they're going to have more sheet structures with the layers compared to a different arrangement. These guys can be affected by chemicals, which is why you can take a pill to poop, or take a pill not to poop, or pill to pee, or a pill not to pee. Hormones, okay, so estrogen is going to rise, progesterone drops, you have a period or a baby, depending on who's in your uterus at the time, right? Yes, there's the exact same mechanism. Rise estrogen, lower progesterone, uterine contractions. If you happen to have a baby, it's called birthing. If you don't have a baby, it's called a period. Okay, so same thing going on with those. It's hormones. And then local contractions. Your smooth muscle gets excited because the guy next to him gets contracted. So we actually see this a lot with females. A lot of females will get period poops. Not all females like to talk about their issues, but it is something that many women, when it's time to have a period and their uterus is contracting so they can have a period, their large intestine goes, me too, I want to contract, and you'll poop, okay? This is why sometimes women will poop during birth, because the large intestine goes, me too, I got something, and they're like, oh, bag catches everything, okay? So we were able to have period poops because the local contractions of the uterus cause local contractions of the large intestines, and everybody gets in on the game down there. So examples of our visceral smooth muscle, of course, the digestive system, gallbladder, urinary bladder, female reproductive system to get rid of stuff, that kind of stuff. Big bad hairy question? Oh, disorders, are you excited? The end is near. All right. Muscular dystrophy. This is a hereditary disorder. So here, the person cannot build the protein dystrophin properly. So that's why it's called muscular dystrophy, because your dystrophin protein's messed up, protein of it. So we didn't talk about the role of dystrophin in muscle contraction because, good gosh, we've talked enough about all the proteins. We don't need to add another one, right? No, I don't want to talk about it. Okay, so this is a part of the muscle cell membrane that helps does interact with our muscle contraction. So what happens when somebody has muscular dystrophy? This protein does not work properly. Eventually, your muscles will not contract properly, and you'll stop moving. Okay, so it will be fatal depending on the type of dystrophy you happen to have. Some are faster killing than others. So you end up with paralysis. Myasthenia gravis. This is an autoimmune disease. So again, your autoimmune disease is when your body just decided you're the enemy and it's going to kill you. Okay. So in this case, it's going to attack the neuromuscular junction. So when it attacks the neuromuscular junction, it prevents the neuron from releasing as much acetylcholine because it's being attacked. It's just like if you go to a fort and you attack it, it's harder to send shipments out of that fort because it's under attack. Not only are we under attack and not releasing a lot of acetylcholine, we may end up with excessive amounts of acetylcholinesterase, the enzyme to break down acetylcholine. So that's going to cause acetylcholine not released or broken down too quickly to fully stimulate those muscle cells. So it causes weaker stimulations, weaker muscle contractions. So you'll have muscle weakness and eventually you'll have paralysis. The easiest way to test for this without doing blood testing is to tell the patient to look up, okay? Because your eyes, again, only have fast fibers. When you look up, if you don't have this condition, you can look up indefinitely if you want to. But unfortunately, if you do have this condition, eventually the neurons won't be able to release enough acetylcholine to maintain contraction, and your eyes will start wandering. They won't keep looking up. They'll just wander around like a cartoon eyeball. And of course, if the eyes aren't doing what they're supposed to, that's an indication that there's weakness in those muscles. And if your weakest of the weak muscles are showing symptoms, then your other boys are probably showing it as well. Okay, so you'd be on immunosuppressants so you don't have muscle weakness and you can still have mobility. Hernias. This is one of the times when your organs pop out and says hello. So you have the abdominal pelvic viscera that will pop out, either pop down, pop out, pop up. We'll get more into hernias on test 4, give you something to look forward to. Yay, hernias. Okay. Muscle soreness, as we talked about, is often due to lactic acid buildup, too much oxygen debt. This can lead to edema because as that muscle is leaking the lactic acid into the surrounding connective tissue, it creates an imbalance of electrolytes, which causes water to try to dilute that. So if somebody is like, oh, I exercise so much, my muscles are swollen. Technically, the muscles aren't swelling. The muscle cells are not swelling. It's the connective tissues by it that are swelling. The endomycin is swelling and the perimycin is swelling because of that fluid shift to try to wash away the lactic acid. Botulism or Botox, these are the exact same thing. One is wild when you don't cook your food properly, and the other one is you pay someone to shove it into your face. So what happens? The Botox or botulinum bacteria produces a toxin that prevents the release of acetylcholine at the neurotransmitter or at the neuromuscular junction. So if you can't release the neurotransmitter, you can't stimulate the muscle cell, you have muscle paralysis. So you get Botox in your face to get rid of your wrinkles because your wrinkles are caused by muscle contractions. The more your muscle contracts, the more it bends your skin, the bigger your wrinkle is going to be. Okay, so that's why we tend to have frowny lines, or you get the line between your eyes or what have you, because you have that repeated scalp. So if you can't contract, you can't bend the skin, the wrinkles go away. And that's why it always comes back. It wears off eventually. You're going to be able to move your face properly again, and then the wrinkles will come back. So you have to do Botox every 6 months, every year or so to keep it down and keep it suppressed. Or just don't have any emotions. That'll work.
So just relaxing your face can help get rid of.
You just have to be willing to not have any facial expressions. And then everybody goes, "What's wrong with you?" And then you make the face, and you're like, "There's the wrinkles." You keep asking me what's wrong. We can get this again from food poisoning. So either improper canning. This is why they always tell you if you can, you've got to boil your stuff beforehand. Make sure it's all sealed. If the little pop top is popped, don't eat it because somebody else has already eaten it. So that's what happens with that gut. You can also get it with smoked foods. So there's a difference between cold smoking and warm smoking. One of it preserves the meat, cutting down bacterial. One just imparts flavor. So sometimes when you have smoked food, it still says cooked thoroughly. Like, bacon is smoked. Nobody eats bacon raw. It's in the thing. So we want to make sure we cook our food properly. And if it's canned, we want to make sure the cans aren't dented or popped or anything like that, because those bacteria are in there eating, and they're going to be making this toxin. Of course, if you eat it, one, it paralyzes your smooth muscles. So that's not going anywhere. You'll have a big backup in the system because your stomach can't empty. And of course, it doesn't just stay in the digestive system. It spreads to surrounding tissues. And what's right next to your stomach is your diaphragm for breathing. So if you paralyze your diaphragm, you can't breathe, you die. So that's how you die from that type of food poisoning, is you can't move the digestive system, and eventually you can't move the body. So paralysis. That's why you got to have those tame Botoxes from the labs. They raise Botox to be weak, so it just gets rid of your wrinkles, versus the wild version that will eat you. You have to between a chihuahua and a wolf. Breeding. So don't buy something off the internet and put it into your body, which is good to know, right? Do not buy anything off the internet to put into your body. You can get Botox on eBay and stuff. It doesn't mean that it's safe Botox. It could be wild Botox. Oh my God. Don't do it. Just say no. Oh, look at that. We're done. So that means tomorrow we get a review before your test that opens on Wednesday, closes Thursday.
Of what we've been going over the past 3 days or 4 days?
Technically, it'll be
5 days.
Yeah.
Exactly.
A lot of the days.
Oh, no.
Yeah, so we'll be going over the stuff on test 3, appendicular skeleton, articulation muscle tissue. Some of it will look a little familiar because it's almost like we just had a lab test over